Hello and welcome to tutorial 2 on non-Gaussian measurements presented by NavAbility. This tutorial will go through the Julia NavAbility SDK version of the API. If you haven't already looked at the tutorial 2 welcome video, please have a look at it as it gives some introduction and background information. There are many ways in which non-Gaussian measurements occur. This tutorial will simply pick one example to illustrate the basic concepts. In short, measurements do not have to follow a unimodal bell curve, but can instead introduce non-Gaussian beliefs. We ground this tutorial in an example. Imagine a wheeled robot traveling in a straight line. We use wheel encoders for the factors to estimate the distance traveled. However, from time to time the robot gets stuck and the wheel spins for a free rotation before progress continues. Let's get started by adding the required package. The only required package is the NavAbility SDK. If you are running a local solution or the required package is not available for some reason, you can simply use the package manager as shown here and add the NavAbility SDK package. The first thing we have to do to build our factor graph is create a user ID guessed at navability.io, a robot ID that can be anything that you want. Here we just use SDKGL and an automatically generated string. Next we need a NavAbility HTTP client and we create a session ID named tutorial2. Using the robot ID, user ID and session ID we can create a content that will be used to identify our robot. Since the SDK works asynchronously, we are going to collect the results in a vector of tasks. The first variable we are going to add is of type continuous scalar, and we are going to name it x0. We simply call add variable with the client content, the variable name x0, and the variable type continuous scalar. We give our robot an initial starting point, a unary factor, taken here as a normal with 0 mean and a standard deviation of 1. We call add factor with our client content, the variable name that the factor should be attached to, and our factor type, which is a prior with a normal distribution of 0 mean and a standard deviation of 1. Let's go have a look at the graph we have so far. You can do that by going to the NavAbility app and as you see here we have the factor graph topology with the variable x0 we just added and the prior that's attached to it. Next, let's add a second variable x1 and connect it to x0 with a relative factor. Here we add the variable x1 of type continuous scalar and we connect x0 to x1 using a linear relative factor with a normal distribution of 10 units and a standard deviation of 1. As with tutorial 1, we can visualize the belief states over any of the variable nodes. This block waits for the completion of our added variables and factors and then triggers a new solve. Once the solve completes, we can look at the results in the NavAbility web app. Follow this link to go to the NavAbility web app. Since we now work with one-dimensional variables, click the Show Distributions button. And I also like to use the show clown colors to color the different variables. We can now see that the variable x0 is located at position 0 as expected, and x10 is 10 units from x0 from the relative factor that we added to it, with a broader distribution. The predicted belief of x1 is nothing more than the approximated convolution of the current marginal belief of x0 with the convolutional belief described by our linear relative factor that we added. Thus far, the tutorial has used parametric noise models, but the solver can easily consume non-parametric measurements as well. These include kernel density estimates, intensity maps, and more. Here we are going to use a mixture model to capture the accuracy of the wheel slip detection. We first add a new variable, x2, also of type continuous scalar, and then create a new linear relative factor that we want to place between variable x1 and x2. The linear relative factor will be of type mixture with a slip and a non-slip probabilities of 40% for the slip case and 60% for the non-slip case. For the slip case, we use a Rayleigh distribution, and for the non-slip case, a uniform distribution. Since we know very little of the non-slip case, let's take the robot distance traveled as uniformly distributed somewhere between 40 and 60 units. Let's trigger a new solve on the NavAbility platform. The MMO factor we just created illustrates how a near arbitrary mixture probability distribution can be used as a conditional relationship between variable nodes in the factor graph. In this case, a 40-60% balance of a Rayleigh and a truncated uniform distribution, which acts as a multimodal conditional belief. If we go to the geometric map again, we can see what exactly this means. If you haven't already, click Show Distributions and Show Clown Colors. You should now see the addition of the x2 variable and its distribution. Here it's illustrated in green. As you can see, the variable x2 clearly has two modes caused by our mixture model. The first mode is located at around 15 units, and that was caused by the Rayleigh distribution. The second part in our mixture, the uniform distribution, causes the second mode in the range of 45 to 65-ish units. The mode near 20, the Rayleigh one, is associated with the slip mode case, and the other mode that's near 60 is associated with the non-slip mode. In suspecting that the wheels did indeed slip, we reverse the robot 50 units and add a new variable x3. Here we add the new variable x3 of type continuous scalar and a new factor of type linear relative between variables x2 and x3 with a normal distribution of -50 units. This part of the tutorial shows how a unimodal likelihood, a conditional belief, can transmit the bimodal belief currently contained in x2. Let's solve the graph again and have a look at the results. Notice the x3 trace is a shifted and slightly spread out version of the belief on x2. To get a more precise marginal belief estimate for each of the variables, we can introduce more information into the factor graph. We add a factor directly from x3 to x0 as a final piece of information. Pay close attention to what this last factor means in terms of probability density traces shown in the previous figure. The trace for x3 has two major modes, one that overlaps with x0 and x1 near 0, and a second mode further to the left at -40. The last factor introduces a shift of 40 units, which essentially aligns the leftmost mode of x3 back onto x0. Global inference over the full graph can now be triggered. Again, we use solve session to trigger the final solve in the NavAbility platform. Let's go have a look at our new factor graph topology. We have variables x0 to x3 with a prior connected to x0 as before, but we now have a new factor that closes the loop between x0 and x3. You can also solve the graph again to demonstrate a stable solution. To get the resulting posterior marginal beliefs over all the system variables, you can use get variables and extract the parametric point estimates from them, as shown in this block. If you look at the result, it turns out that the wheels did indeed slip. The resulting distance from x1 and x2 with all the data available turns out to be 10 units. This is much less than the 60 units measured by the encoder. This means that the slip mode case survived, and the non-slip case disappeared. This example is constructed in such a way that when all data is considered together, a clear mode can be extracted. In real situations, the belief could be more nuanced, which is all the more reason to consider non-Gaussian estimation, which permanently keeps track of nuanced features hidden in the data. In conclusion, it is important to note that although this tutorial ends with all marginal beliefs having near Gaussian shapes and unimodal, that the package supports non-modal belief estimates during both the prediction and global inference processes. That concludes tutorial 2. The next tutorial looks at weakly observable situations where all Gaussian measurements results in highly non-Gaussian and multimodal posterior estimates. Also have a look at the marine surface navigation case study linked in the tutorial.